Okay, now third page. Projectile-like motion of charged particles in a uniform field. So motion, the parallel to electric field, is accelerated. Use acceleration equations from Physics 20. So when we have, say, a parallel plate, up to these questions, we had just, like, say, the electron coming in and it went like across like that. But when you're told that it's accelerating, okay, it generally is coming in, say, here. And say if this is the positive end of the plate, this electron is going to accelerate up like that. And so it's going to be like projectile motion going up, okay? When you have projectile motion, remember your horizontal, if whatever speed it tells you it starts at, that's like your horizontal, and that it stays. Your horizontal stays throughout the whole thing, okay? So think about horizontal. You use V equals D over T, and this is principle 0 of on your data sheet, okay? Then when we're dealing with vertical, okay, you can use your acceleration formulas, and this is principle 1. Okay? So that's when, okay, there's probably hardly any, and then we increase, okay? So the vertical vectors are increasing because we're accelerating. Okay, blah, blah, blah. We can use forces or energies to solve these types of problems, but be careful with using energies and voltage because the voltage is changing between the plates at different distances. The force of gravity can be ignored for atomic or subatomic particles, like protons, electrons, alpha particles, etc. Therefore, F net is equal to Fe and Fg, okay? So motion perpendicular to the electric field is uniform. Just like I said, that's horizontal, right? I should use horizontal. Okay, you only use V equals D over T. The particle already had some perpendicular speed. It shot into the area. Time is the same between parallel and perpendicular motion. So that's like the variable that you can have on either side. There's going to be a couple questions about current, where current is equal to the charge over time. And then you have your Millikan's oil drop. So you always start with a free body diagram to determine the direction of forces acting on the particle. The force of gravity cannot be ignored because the oil drop is not a subatomic particle or an atomic particle. So the force of gravity is significant and you need to include it. So the only time, though, that Fe is equal to Fg is if you are told that the particle is stationary or it's moving at a constant velocity. So you can use EQ is equal to mg. So scenarios like that would be as such. So here's 2 examples. So say I have this top one, there's negative, and then positive on the bottom. And in this example, or I have positive on the top and negative on the bottom. So say, for instance, I have an oil drop that is positive, okay? It's going to be, it will have an Fe that attracts it up and an Fg pulling it down, okay? If both of these vectors, the magnitudes, are the same, it will be stationary or just moving at constant velocity. Say, though, your oil drop is negatively charged, and you'd be told, or it could be determined, and it would have a charge or a force pulling it up because it's attracted to the positive, and Fg going down. So it just depends on the question and how the plates are arranged and what charge your particle is. But these are the 2 scenarios in which Fe could equal Fg. All right, so next, say the particle is accelerating downward. So this is where you have F of E plus Fg is equal to your F net. So our 2 scenarios, So I'll draw my plates here. Again, negative on top, positive on the bottom, or positive on the top and negative on the bottom. Okay, so say I have a positive particle here. Sorry, I'm actually going to put a negative here. So it will have an Fe pulling it down, but it will also have Fg pulling it down. So that's why we can add those two together. We're always adding them together, but it's just that they're both, you could label them both as negative, or you could just reference negative, or reference them as both positive. It doesn't matter. You're going to be adding them both together. You just have to know that the force is going down, though. You know, so you could say, if you would prefer, you could say this is F net is equal to negative Fe plus negative Fg. Okay, if you'd prefer that. Okay. Or so say if we have a positive here, it's going to be pulled down by electrical force and gravitational force. Okay. And my last example, okay, is if we had Fe plus negative Fg, so if they were working in opposition. So if Fg was smaller in magnitude than Fe, okay, and they're going the opposite direction, okay. Same thing. If I have positive on the top, negative on the bottom. My Fe needs to be larger than Fg, and you ask maybe why? Well, because if they were the same, it would be stationary. It wouldn't be accelerating up. Okay, so they need to be different magnitudes. That's why we draw our arrows with different magnitudes. Okay, so now you should be ready to do your questions. I'd like you to have your Millikan's oil drop questions done, your workbook, but don't hand it in. Take it home, study it. I think we will have our test on Wednesday. I'd prefer, because then you can ask questions. All right, so work hard. Happy studying. See you later.